Welcome to Statistics for Surveys Session 2 Tables, Optional Segment 5 Frequency Density with a Standard Bin Size. In this segment I'll try to explain how you can use a standard bin size instead of a unit size when calculating frequency densities. It can be helpful if you watch the tables for a scale variable video already, so you're familiar with the term frequency density. To quickly recap what frequency density was, it was used to see which bin is most crowded and is the frequency that would be in each subbin if a bin was actually split up into these subbins with a size of 1. It's calculated by taking the frequency and divided by the bin size. So here's an example where, for example, 8 people scored between 5 but under 7. And the bin size is the 7 minus the 5 to get actually 2. And the frequency density is then the frequency divided by the bin size, 8 divided by 2, in this case 4. This 4 in itself is actually, if we would split up the 5 but under 7 category in sizes of 1, so bin size of 1, and the total should therefore still remain that 8, and therefore indeed each of these gets a frequency of 4, which is therefore the frequency density up here. Note that if we have a few of the bin sizes that are all the same, then we're actually doing quite some calculations that are each time the same. And this can be avoided by using this so-called standard bin size. To understand a little bit the concept of a standard bin size, I'll go back to the idea of population density, which was the population per square kilometers. However, you might imagine this can also be per square mile, per square meter, or any measurement you like in there. So the same we can apply to the frequency density, where instead of using a bin size of 1, we can actually use all kinds of different standards, if you will. So we can also say that it's the frequency that would be in each subbin if a bin was split up into bins of size with a standard bin size. How this can be achieved I will show you on the next slide. So here's a table where standard bin size has been used. The first thing to actually notice is the bin size themselves. The one that occurs most often, in this case 2, is usually set as the standard bin size. That's also what I will do in this example. However, it's not compulsory. You can choose any standard bin size you like. However, you're doing this to avoid some calculations, and you will avoid the most calculations if you use the bin size that is actually occurring the most often. The next thing to do is now to see how many of these bin size actually go into bin sizes that are not the standard. So the first drinks category has a bin size of 1, which is therefore only half of a standard bin size. And the last two the same. This one has a bin size of 4, and that's therefore 2 times a standard bin size. And the last one has a bin size of 8, which is actually 4 times the standard bin size. The frequency density is now calculated by taking the frequency and dividing it by the number of standard bins. So for the first one, we'll take the frequency, we'll divide that by the number of standard bins, and that gives us 12. Note that 6 divided by 2 would be 3, but we're doing 6 divided by a half, which is actually 12. For bins that actually have the standard bin size, we don't need to do any calculations because we're simply dividing by 1. So these actually remain the same. Here's where we actually win in time from using the traditional unit size, because now we don't have to do any calculations on these. The second to last one is actually 10 divided by the number of standard bins, which was 2, so we actually get 5. And the last one is 10 divided by 4, which will give you the 2.5. So what does this actually mean, for example, this 5? Well, it's similar as with the interpretation of the regular frequency density. If we have a look at this one, 7 to 11, With the normal frequency density that we've done in the past, we would split this up into groups of 7 but under 8, 8 till 9, 9 till 10, and then 10 till 11. And now we can do the same, but actually splitting them up in the standard bin size, which was 2. So 7 plus 2 equals 9, 9 plus 2 equals 11, and these two together are then the same as 7 but under 11. The total of these two groups combined should of course be 10. So again here we say plus and should be 10. And since we only have 2 bins, that means that each of these gets a frequency of 5. And that's exactly this 5 here as the frequency density. Let's do that again for the next category, the 11 but under 19. We can actually split this up into bin sizes of 2 again. 11 plus 2 equals 13, 13 plus 2 15, 15 plus 2 17, 17 plus 2 19. Altogether these should actually add up to 10 again. So here it should be 10. And indeed 10 divided by 4 equals 2.5. So 2.5 for each, and that's exactly this 2.5 over here. We see now two methods to calculate frequency densities. One is to use the unit size, which is actually a standard size of 1, and the other one is to use anything else as a standard size, and in this example I've used 2. Notice that the results are actually simply a multiplication of each other. So if you take the unit size and multiply it by the standard size used, you actually get the frequency densities using that standard bin size. This means that the lowest number, in this case 1.25, will actually remain the lowest number, and the other way around, the highest number will still remain the highest number, and proportions also stay the same. So the most crowded, because we're often using frequency density to see where it's most dense or least dense, or in other words, most crowded or least crowded, that stays the same. So that's why both of these methods are still actually valid, and you can use either one of them. If you use a standard size different than 1, please make a small note underneath the table to let your reader also note this. The advantage of using this standard size is that for all the bins that have this standard size, we don't need to perform any calculations on these because they're exactly the same up here. While if we would not use a standard size, we would still have to perform 3 calculations, in this case 16 divided by 2 to get 8, 12 divided by 2 to get 6, and 8 divided by 2 to get 4. So it saves some time when using a standard bin size in the calculations, but on the other hand, it depends. If you're using a computer, then it doesn't really change so much. It can also help if, for example, the bins are extremely large, because then the frequency densities might get extremely small. So then you perhaps can use a standard size of, let's say, 1000, so that the frequency densities won't have so many decimal points.